Okay, everyone. I said last class that I would put up a video to help reinforce and practice how to calculate the pH of a salt solution. So we're going to go through questions 3 and questions 4 from the last KA, KB skill sheet. So let's start out with question 3 on the practice 1 side. So it's asking us to calculate the pH of a 0.3 molar sodium fluoride solution. I'm kind of cool that this is the stuff that you'll find in toothpaste most often. So you find out like, oh, I guess that stuff's actually a little acidic or basic. Huh, that's weird. So we're given that HF has a Ka of 7.2 times 10 to the negative fourth. And I told you a little trick here is if they give you a Ka, it means we're probably solving up something for a basic solution. So I'm just going to jot that down. That's my little hint. And how do I know this isn't just a straight weak acid, weak base problem? Is that I have sodium fluoride, and that's not an acid we're used to seeing. It's not a base we're used to seeing. It's a salt. So when we have that positive ion with the negative ion, we have a salt here. So to start this problem off, number 1, I'm going to think about what happens when I have a base with Na in it. So the base with Na in it would be NaOH. Now that's a strong base, so we're not going to get any partial dissociation there, no going back to the reactants. So I'm going to cross the Na out there. That's not going to lead to a acidic or basic solution here. So what about that F? The acid that would be paired with fluorine would be hydrogen fluoride or hydrofluoric acid, and that is a weak acid. So this is going to be the thing we're going to focus on here. So let's start by writing down our F minus. That's going to be the start of this problem. Now, as I've shown you, what we're going to do is pair that with water. Now, looking at the F minus with water, I don't think there's any chance that we think that the F minus is donating a proton or an H plus. It doesn't even have one there, so it's got to be accepting that. So in this case, we're going to have it accepting an H from the H2O. So we're going to get HF on this side plus OH minus. Yep. It's making an OH minus in water, so that kind of confirms that we're dealing with a basic solution here. So step 2, since we're dealing with the basic solution, we need to figure out what Kb is. Now, if F minus is the conjugate of this weak acid, we're just going to do 1 times 10 to the negative 14. That's the K for water, Kw, divided by the Ka here, 7.2 times 10 to the negative 4. Now you plug this in your calculator, and our Kb is 1.4 times 10 to the negative 11. Okay, now, third step, we're going to set up our ice table. And it's going to be very similar to the ice tables we were setting up for our weak acids and bases. We're going to have a number here. We're going to start with 0. We're not dealing with any common ion here. This is always going to be going down. These two will be going up. 0 plus x is x. And then our number here was 0.3 molar. And again, Na and F are 1-to-1 ratio, so this would be the same value. I think that's what we're going to experience here. And I told everyone in class that we're not going to really encounter the situation where x is really changing this value. So we're going to say x is negligible here. So although we have 0.3 minus x, I'm just going to get rid of that minus x right away. Okay, now we have our equilibrium concentration, so we can set up K. So Kb, 1.4 times 10 to the negative 11, is going to be equal to x squared over 0.3. Now we solve for x by multiplying 1.4 times 10 to the negative 11 by 0.3, and then don't forget to take the square root of it. Now we get x is equal to 2.0 times 10 to the negative 6. This is a concentration. Now, if we think about our ice table, oops, I should have actually filled this out. F minus, HF, OH minus. This is what we're keyed in on here. So this X is actually OH minus concentration. So when we do the negative log of X, we're going to be solving for POH and not pH. And then the negative log of that X is 5.7. So I think if you end up with 5.7 as an answer, and we thought that this is a basic solution, that should set off an alarm that this doesn't make any sense. And that should remind you that we need to then do 14 minus 5.7. So we get a pH of 8.3. Also kind of cool that that sodium fluoride solution we're brushing our teeth with is actually helping maybe reduce or increase the pH to more like a neutral pH. Huh, kind of cool. Okay, let's check out another problem here, another salt problem. So on the right side, number 4 here, calculate the pH of a 0.1 molar solution of ammonium chloride. Again, we have ammonium chloride here. This is not something starting with an H, and it's not something ending with an OH. It's not one of those other weak solutions we've practiced. This is a salt again. What might key us in that it's a salt problem is that gives us the Kb for the conjugate here. And if it gives us Kb, it's probably an acidic. It's probably an acidic salt. Let's check this out. Let's look at the two species here, the ammonium ion and the chlorine ion. When the chlorine is with hydrogen, we get hydrochloric acid. Now, again, that is a strong solution, so I am not going to key in on that for this problem. On the other hand, NH4 paired with OH, ammonium hydroxide is a weak base. So that's going to lead to this being a conjugate acid. So this is going to be an acid problem. So step 1, we have NH4 plus ions reacting with water. Now, we've never had NH5 really, so I think in this situation, the water is going to donate the proton or the hydrogen to, I said we're never going to get that. The NH4 is going to be donating the H plus or proton to the H2O. That means we're going to get NH3 here and H3O plus. Yep, this is an acidic problem because we're producing H3O plus in water. Step 2, we need to solve for a Ka here since this is an acid problem. Now, the conjugate here was 1.8 times 10 to the negative 5th, actually, which led to our conjugate. So I'm going to do the Kw on top, 1 times 10 to the negative 14, divide by the Kb, 1.8 times 10 to the negative 5, and that means Ka is going to equal 5.6 times 10 to the negative 10. Step 3, let's set up an ice table. We're going to have our ammonium ion, our ammonia, and our hydronium or hydrogen ion right here. So this is always going to be the value we're given. That's our 0.1 molar. It's a 1-to-1 ratio again, so we can directly say this. These are going to start out as 0. This concentration will go down. These two will go up. The X is going to be negligible compared to the 0.1, so we're just going to say 0.1 molar minus X. We can just ignore the minus X. 0 plus X, we get X for both of these. And now we have our equilibrium concentrations. And with equilibrium concentrations, we can set them equal to K, which was 5.6 times 10 to the negative 10. So that's going to equal X squared over 0.1. We multiply 5.6 times 10 to the negative 10 times 0.1 and then take the square root. And we find that X is equal to 7.5 times 10 to the negative 6th. Now looking up here, X this time is the concentration of H plus / H3O plus, our hydronium ion. So when that is the case, the negative log of X this time will just be equal to pH. So when we set that up, we find that pH is 5.1. We look back at our problem, and this was an acidic solution, so I think 5.1 makes sense. So again, with these salt solutions, first step, figure out which species might lead to an acidic or basic solution. Add that to water and find out what we're producing. Find the K value we need. You're always going to be dividing that from 1 times 10 to the negative 14. Step 3, set up an ice table to get your equilibrium concentrations. Step 4, solve for X. And then step 5 is calculate the pH using that X. Okay, I hope this helped. Check your work and good luck reviewing.